welcome to this problem walkthrough. Today, we'll be tackling problem number 2032, 2 out of 3. This problem challenges us to analyze 3 arrays and identify the integers that appear in at least 2 of them. It's a great exercise to practice problem solving and working with hash maps. Let's dive into the details and explore the solution approaches. In this problem, titled 2 out of 3, we are given 3 integer arrays, nums1, nums2, and nums3. Each array may contain duplicate values. Our goal is to return a list of all distinct integers that appear in at least 2 out of these 3 arrays. The order of the result does not matter, so any valid order of the answer is acceptable. Looking at the input format, nums1, nums2, and nums3 will each have a length between 1 and 100. Additionally, the values within these arrays will lie between -100 and 100. The output, as mentioned, must be a list of integers, and the integers should be distinct, meaning no duplicates in the result. Let's explore some examples to better understand what this means in practice. In the first example, we have nums1 as 1, 1, 3, 2, nums2 as 2, 3, and nums3 as 3. The output for this input is 3, 2. Here's why: the number 3 appears in all 3 arrays, while the number 2 appears in both nums1 and nums2. Since both of these numbers are found in at least 2 of the arrays, they are included in the result. Remember that the output order doesn't matter. 3, 2, and 2, 3 are both valid answers. Now, let's consider another example to further clarify. In the second example, nums1 is 3, 1, nums2 is 2, 3, and nums3 is 1, 2. The output here is 2, 3, 1. This is because the number 3 is present in both nums1 and nums2, the number 1 is found in nums1 and nums3, and the number 2 is shared between nums2 and nums3. All 3 numbers meet the condition of appearing in at least 2 arrays, so they are included in the result. Again, the order of the output does not matter. Finally, in the third example, nums1 is 1, 2, 2, nums2 is 4, 3, 3, and nums3 is 5. The output is an empty list, because no integer appears in at least 2 arrays. In this case, there are no overlaps between the arrays, so the result is simply an empty list. Let's now consider the constraints and edge cases to make sure we fully understand the problem. The total number of elements across all 3 arrays will not exceed 300, so the combined length of nums1, nums2, and nums3 will always stay within this limit. Each integer in the arrays will fall between -100 and 100. Importantly, the result must contain distinct integers, meaning duplicates in the input arrays should not affect the output. For edge cases, if the arrays contain entirely disjoint sets of numbers, the output will be an empty list. If there are multiple duplicate values in a single array, such as 1, 1, 1 in nums1, we treat it as if the value 1 appears only once. Negative integers are also valid, and the solution should handle them correctly. For example, if nums1 is -1, -2, nums2 is -2, -3, and nums3 is -1, -3, the output should be -1, -2, -3. Additionally, if all 3 arrays are identical, the result should include all distinct values from the arrays. Lastly, minimal input sizes, such as arrays with just 1 element each, should be handled properly. For instance, if nums1, nums2, and nums3 each contain the number 5, the output should simply be 5. To start, let's consider the brute force approach. The intuition here is straightforward. We manually check each integer in the 3 arrays to determine if it appears in at least 2 of them. This involves using nested loops to compare elements across nums1, nums2, and nums3. As we find integers that meet the condition, we keep track of them, ensuring that only distinct integers are included in the result. While this approach is simple to understand and implement, it's computationally expensive because the repeated comparisons require multiple iterations through the arrays. For larger inputs, this inefficiency becomes a significant drawback, with the time complexity reaching approximately n squared. This makes it impractical for scenarios involving large datasets. Now, a more efficient approach involves using sets. By leveraging set operations, we can streamline the process of identifying common elements across the 3 arrays. First, we convert nums1, nums2, and nums3 into sets, which automatically remove any duplicates. Then, we compute pairwise intersections such as finding the common elements between nums1 and nums2, or nums2 and nums3. These pairwise results are combined to ensure we include integers that appear in at least two of the arrays. The beauty of this approach lies in its simplicity and speed. Sets inherently eliminate duplicates, and their intersection operations are highly efficient. Converting arrays to sets is O(n), and computing the intersections adds minimal overhead, leading to an overall time complexity of O(n). This makes it an optimal solution for the problem. Another viable option is the frequency mapping approach. Here, the idea is to count how many arrays each integer appears in. To achieve this, we use a dictionary to track the count of each integer. As we iterate through each array, we ensure that an integer is only counted once per array by using a set for each array's elements. Once all counts are recorded, we simply extract the integers that appear in at least two arrays. This method is also efficient, with a time complexity of O(n), as it involves iterating through the arrays and performing dictionary operations. While effective, this approach requires additional logic to avoid double counting integers within the same array, which adds a layer of complexity compared to the set-based solution. The chosen strategy for this problem is the optimized set-based approach. This solution stands out for its combination of efficiency and simplicity. By leveraging mathematical set operations, we eliminate duplicates and simplify the process of finding intersections, avoiding the complications of frequency tracking or the inefficiencies of nested loops. Pairwise intersections allow us to focus on the core requirement, identifying integers present in at least two of the arrays, while keeping the implementation clean and straightforward. Comparing the approaches, the brute force method is too computationally expensive for large inputs, while the frequency mapping approach, though efficient, requires additional checks to prevent double counting. The set-based approach strikes the perfect balance, achieving optimal performance with minimal complexity. The key insight, or aha moment, was realizing that sets naturally handle duplicate elimination and intersection checks, making this the most intuitive and efficient solution for the problem. The problem requires us to work with three arrays, nums1, nums2, and nums3. Our task is to identify all integers that appear in at least two of these arrays. Importantly, the result should only include distinct integers, meaning no duplicates, even if duplicates exist in the input arrays. For example, if nums1 contains 1, 2, 3, nums2 contains 3, 4, 5, and nums3 contains 5, 6, 7, the integers 3 and 5 meet the condition because 3 appears in nums1 and nums2, while 5 appears in nums2 and nums3. Therefore, the output would be 3, 5. To solve this efficiently, we'll use sets, as they allow fast lookups and automatically handle duplicates, making it easier to determine which integers meet the criteria. Using sets simplifies this problem significantly. First, sets handle duplicates for us, so we don't need to worry about manually filtering out repeated elements within an array. Second, set operations like union and intersection allow us to easily identify overlaps between arrays. To begin, we convert each array into a set to eliminate duplicates. For example, nums1 becomes set 1, nums2 becomes set 2, and nums3 becomes set 3. Once we have these sets, we can calculate pairwise intersections using the set intersection operator, denoted as AND. For example, we calculate common 1 as the intersection of set 1 and set 2, common 2 as the intersection of set 2 and set 3, and common 3 as the intersection of set 3 and set 1. In the case of nums1 equals 1, 2, 3, nums2 equals 3, 4, 5, and nums3 equals 5, 6, 7, we would have set 1 equals 1, 2, 3, set 2 equals 3, 4, 5, and set 3 equals 5, 6, 7. Then, common 1 gives us 3, common 2 gives us 5, and common 3 gives us an empty set, as there are no integers common to nums3 and nums1. After calculating the pairwise intersections, the next step is to combine all the common integers. This can be done by taking the union of common 1, common 2, and common 3 using the set union operator, represented by. This union will give us all integers that appear in at least two of the three arrays. For example, if common 1 is 3, common 2 is 5, and common 3 is an empty set, the union of these sets results in 3, 5. Finally, we convert this set into a list to meet the output requirement. Optionally, we can sort the list to ensure consistent order, though sorting is not mandatory for correctness. Using sets not only simplifies our logic but also makes the algorithm efficient. Converting the arrays to sets is linear in time complexity, and set operations like intersections and unions are optimized for performance. This approach also handles edge cases, such as when the arrays are empty or when no integers meet the condition, resulting in an empty list. Edge cases are an important consideration in this problem. If all three input arrays are empty, the result is an empty list since there are no integers to compare. Similarly, if no integers appear in at least two arrays, the result is also an empty list. On the other hand, if all integers appear in all three arrays, the result will include all distinct integers from the arrays. The data structures we use further clarify the solution. The input consists of three integer arrays, while the intermediate steps involve converting these arrays into sets to store unique values. Pairwise intersections are used to identify overlaps between sets, and the final output is a list containing the distinct integers meeting the criteria. In terms of complexity, the time required to convert arrays to sets is proportional to their lengths, which is O, n1 plus n2 plus n3. Calculating intersections and unions is efficient, with a time complexity governed by the size of the smaller sets. The space complexity is determined by the storage of sets and intermediate results, which is also O, n1 plus n2 plus n3. This approach ensures our algorithm scales well with input size. The final Python implementation of the solution is both concise and efficient. We start by converting the three input arrays into sets to remove duplicates. Then, we compute the pairwise intersections, common 1 for elements shared by nums1 and nums2, common 2 for nums2 and nums3, and common 3 for nums3 and nums1. The union of these intersections gives us all integers that appear in at least two arrays. Finally, we return the result as a list. For example, given the input nums1 equals 1, 2, 3, nums2 equals 3, 4, 5, and nums3 equals 5, 6, 7, the sets are set1 equals 1, 2, 3, set2 equals 3, 4, 5, and set3 equals 5, 6, 7. The intersections are common 1 equals 3, common 2 equals 5, and common 3 equals an empty set. The union of these gives 3, 5, which is returned as the list 3, 5. This solution is robust, handles edge cases effectively, and operates efficiently within the constraints of the problem. The given problem requires identifying integers that appear in at least 2 out of 3 input arrays. The approach uses Python sets to efficiently compute intersections and unions, ensuring distinct values are handled correctly. The first step is to convert each input list, nums1, nums2, nums3, into a set. This eliminates duplicate values within each list and allows for set operations like intersections and unions. Next, the code computes elements common to at least two sets. This is achieved by taking the intersection of each pair of sets, set1 and set2, set2 and set3, set1 and set3, and combining the results using the union operator. The union ensures no duplicates appear in the final result. Finally, the combined set of all valid elements is converted back to a list, which is returned as the output. This ensures the result meets the problem's requirement of returning a list of integers. This solution is efficient, as set operations like intersection and union are performed in O, min, len, set1, len, set2, time for each pair. The overall complexity is linear with respect to the total number of unique elements in the input arrays. This implementation is clean, concise, and handles all edge cases effectively, including empty arrays or arrays with duplicate values. Here, we start by importing the necessary utility classes from Java, including java.util*, which will help us use data structures like hashset and arraylist. We define a class called solution with a method 2 out of 3 that accepts 3 integer arrays as its parameters. The goal of this method is to find all the integers that appear in at least 2 of these arrays. To achieve this, we use 3 hashset objects set1, set2, and set3 to store the unique elements from each input array. Each for loop iterates over one of the input arrays, adding its elements to the corresponding set. This ensures that each set only contains distinct values from its respective array. Next, we define another set called resultSet to store the integers that are found in at least 2 of the 3 sets. We then loop through the elements of set1 and check if the current element exists in either set2 or set3. If it does, we add that element to resultSet, ensuring that our results only include numbers that meet the problem's criteria. We continue by iterating through the elements of set 2. For each integer in this set, we check if it also exists in set 3. If so, we add it to result set. By doing this, we account for any numbers that appear in the second and third input arrays but were not present in the first. Finally, we convert the result set into a list using the ArrayList constructor and return it as the output of the method. This ensures that the result is returned in the required list format. By using sets, our approach efficiently handles duplicate values within each array and simplifies the process of identifying numbers that appear in multiple arrays. This implementation is both concise and effective for solving the problem. To solve the problem, we start by initializing the input arrays, nums1, nums2, and nums3, as provided in the example. The first step is to convert each array into a set to remove duplicate values and make the comparison process more efficient. For nums1, we create set 1 containing the unique elements 1, 2, 3. Similarly, nums2 becomes set 2 with 2, 3, and nums3 becomes set 3 with 3. Next, we find the common elements shared between these sets. We calculate the intersection of set 1 and set 2, which gives us 2, 3. Then, we find the intersection of set 2 and set 3, resulting in 3, and the intersection of set 1 and set 3, which also results in 3. Finally, we combine these results using the union operation to ensure we capture all elements that appear in at least 2 of the 3 sets. The union of these results gives us the set 2, 3. After computing the combined set of common elements, the next step is to convert the set 2, 3 into a list. This gives us the final result as 2, 3 for this example. Now, let's move to the second example where the input arrays are nums1 equals 3, 1, nums2 equals 2, 3, and nums3 equals 1, 2. Again, we start by converting these arrays into sets. From nums1, we create set 1 containing 1, 3. From nums2, we create set 2 containing 2, 3. Lastly, nums3 is converted into set 3 containing 1, 2. By converting these arrays to sets, we ensure that we eliminate duplicates and prepare for the next step of finding common elements. Now that we have the sets for the second example, we compute the intersections to determine the elements that are common between any 2 sets. First, we find the intersection of set 1 and set 2, which gives us 3. Then, we compute the intersection of set 2 and set 3, resulting in 2, and finally, the intersection of set 1 and set 3, which gives us 1. Once we have these results, we combine all the common elements using the union operation to ensure we include every number that appears in at least 2 of the 3 sets. The union of these intersections gives us the set 1, 2, 3. Finally, we convert this set into a list, resulting in the output 1, 2, 3. This completes the second example. In the third example, the input arrays are nums1 equals 1, 2, nums2 equals 3, 4, and nums3 equals 5, 6. As before, we begin by converting these arrays into sets to eliminate duplicates and facilitate comparisons. From nums1, we create set 1 containing the unique elements 1, 2. From nums2, we create set 2 containing 3, 4, and from nums3, we create set 3 containing 5, 6. Next, we calculate the intersections to determine if there are any common elements shared between these sets. We start by finding the intersection of set 1 and set 2, which results in an empty set because there are no common elements. Similarly, the intersection of set 2 and set 3 also results in an empty set, as does the intersection of set 1 and set 3. Since no elements are shared between any 2 sets, the combined result using the union operation remains an empty set. After determining that there are no common elements in the third example, the final step is to convert the empty set into a list. This gives us the result as an empty list. The output for this example is therefore. This demonstrates how the approach handles scenarios where there are no overlapping elements between the 3 arrays. By converting each array into sets, finding pairwise intersections, and combining the results, we can systematically solve the problem for any input. To analyze the time complexity of our solution, we begin by examining the set construction step. When converting each list nums1, nums2, and nums3 into sets, we eliminate duplicate elements. This operation involves hashing and inserting each element into the set, which takes linear time with respect to the size of the list. If the lengths of nums1, nums2, and nums3 are n1, n2, and n3, the total time spent on this step is O, n1 plus n2 plus n3. Next, we consider the set operations used to find elements appearing in at least two lists. Specifically, we compute three pairwise intersections, set1 with set2 with set3, and set1 with set3. The intersection of two sets takes time proportional to the smaller of the two sets, which in the worst case means O, n1 plus n2 plus n3, for each operation. Finally, we perform a union of the intersection results, and while the exact cost depends on the number of unique elements, it is similarly bounded by O, n1 plus n2 plus n3. After performing the set operations, the final step is to convert the resulting set into a list. This conversion involves iterating through the elements of the result set and inserting them into a new list, which takes O, R, time, where R is the size of the result set. In the worst case, R could be proportional to the total number of unique elements across the input lists, which is O, n1 plus n2 plus n3. Combining the time taken by all steps, set construction, set operations, and list conversion, the overall time complexity of the algorithm is O, n1 plus n2 plus n3, as the processing scales linearly with the size of the input. Now, considering the space complexity, we first account for the memory used by the sets. Three sets are constructed to store unique elements from the three input lists, requiring space proportional to O, n1 plus n2 plus n3. Additionally, a result set is used to store elements appearing in at least two lists. In the worst case, this set also requires O, n1 plus n2 plus n3, space. The final component of the space complexity is the result list, which is created by converting the result set. The space required for this list depends on the size of the result set and is proportional to O, n1 plus n2 plus n3, in the worst case. Therefore, the total space complexity of the solution is O, n1 plus n2 plus n3, as the memory usage is dominated by the sets and the result list. To put this into perspective, let's compare this optimized solution with a brute force approach. A naive solution would involve iterating through all elements of the three lists and checking their occurrences in the other lists. This would result in a time complexity of O, n1 asterisk n2 plus n2 asterisk n3 plus n1 asterisk n3, in the worst case, which is significantly worse than the linear complexity achieved by our set-based solution. The brute force method highlights the inefficiency of repetitive comparisons, especially for larger inputs, whereas the optimized solution capitalizes on the efficiency of set operations. By comparing the optimized solution to the naive approach, we observe a clear trade-off in time efficiency. The optimized solution achieves linear time complexity by leveraging the power of set operations, while the naive approach suffers from quadratic growth due to repeated comparisons. On the other hand, both solutions have similar space requirements in the worst case, as both need to store unique elements. However, the optimized solution balances time and space better, making it more suitable for larger inputs. To understand how the solution performs in different scenarios, we can analyze the best, average, and worst cases. In the best case, the input lists are small and have minimal overlap, leading to fewer set operations and a reduced runtime, while maintaining a linear time complexity of O, n1 plus n2 plus n3. For the average case, we assume moderate input sizes with some overlap, where the complexity remains linear but with slightly larger constant factors due to additional set operations. Finally, in the worst case, the input lists are large, and all elements are unique. While the time complexity is still O, n1 plus n2 plus n3, the constant factors increase because of the greater number of unique elements and more extensive set operations. To formally justify the big O notation, we note that each input list is traversed once to construct sets, and operations like intersection and union scale linearly with the input size. This linear scaling behavior underpins the overall time complexity of O, n1 plus n2 plus n3. Similarly, the space complexity is dictated by the need to store sets and the result list, which collectively require memory proportional to the total number of unique elements. This results in O, n1 plus n2 plus n3, space usage. These characteristics make the solution both efficient and scalable, providing a significant improvement over alternative approaches for this problem. When tackling this problem, there are some common pitfalls to watch out for. One frequent mistake is not accounting for duplicate values within the same array. This happens when the same value is counted multiple times as if it appears in different arrays, leading to incorrect results. The best way to fix this is by using a set to eliminate duplicates within each array before doing any further processing. Another issue arises when you assume that the input arrays are always sorted. The problem doesn't guarantee this, so relying on sorted arrays can cause your approach to fail. To address this, you can explicitly sort the arrays or design a solution that works on unsorted data. Inefficient brute force approaches are another challenge. Directly iterating through all combinations can lead to a time complexity of n cubed, which is impractical for larger inputs. Instead, using hash maps or two-pointer techniques can significantly optimize your solution. Finally, don't overlook edge cases. Examples might include arrays of different sizes, arrays with no common elements, or completely empty arrays. Always test your algorithm against these scenarios to ensure its robustness. Another common mistake is overcomplicating the solution. Adding unnecessary complexity can increase the chances of bugs and make the code harder to read or debug. It's important to keep your solution clear and concise. Now, in interviews, there are some key patterns and strategies to keep in mind. For problems involving multiple arrays, techniques like set operations, hash maps, or sorting combined with two-pointer approaches are often very effective. You should also focus on optimization. Start with a brute force approach to solidify your understanding of the logic, then refine it by reducing redundant checks or leveraging efficient data structures. It's equally crucial to clarify the problem's assumptions. For example, confirm whether arrays are sorted, whether duplicates are allowed, and how to handle edge cases. Lastly, when discussing your solution, emphasize the trade-offs. For instance, explain how you balance time complexity, space complexity, and code simplicity. And don't forget to address edge cases explicitly, such as empty arrays, arrays of different lengths, or scenarios where all elements are identical. Let's now explore some related problems and alternative approaches. Closely related problems include LeetCode 350, which deals with the intersection of two arrays, LeetCode 1213, which focuses on finding the intersection of three sorted arrays, and LeetCode 349, another problem about intersecting two arrays. Additionally, LeetCode 15, the three-sum problem, is a classic example of how to handle multiple arrays efficiently. As for alternative approaches, the hash map method is a standout. Here, you use a hash map to track the frequency of each element across all three arrays. Elements that appear in at least two arrays are part of the solution. This approach is time efficient, with a complexity of n, but the trade-off is increased space usage. Another option is the two-pointer technique, which is especially useful if the arrays are sorted. By traversing the arrays with two pointers, you can efficiently identify common elements. However, sorting the arrays upfront introduces an n log n time complexity. Finally, there's the sorting in binary search method, where you sort one array and use binary search to locate common elements in the other arrays. This can be effective for smaller datasets, but the binary search overhead may make it less ideal for larger arrays. Each of these approaches has its strengths and weaknesses, so choose the one that best fits the problem constraints and input size. Great work! To wrap up, we reviewed the 2 out of 3 problem and highlighted key insights about using hash maps for efficient data tracking. Remember, mastering these techniques will help you tackle similar problems with confidence. Thanks for joining. Be sure to like, share, and subscribe for more coding content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!